So I guess we're gonna start. Today we happy to have Xiaoli Fan. So Xiaoli is one of our colleagues. She works in our department. She's been working for some time now in our department. She has been working on pesticide resistance and also antimicrobial resistance. And today she's going to talk about cost effectiveness of mass drug administration and evidence-based antimicrobial use strategies in food animals. So that's a long title. Xiaoli, you have the floor.
Thank you, Philippe, and sorry about the long title.
That's okay.
I think it's already conveying some information of the research. So this is research together with several colleagues. Yunshuan was an MSc student in REES, and Alan Goddard is another colleague in REES. And Xiaoli Adla is from UIUC. We worked on both pest management and other stuff together in the past. So I'd like to motivate my the research I'm presenting today with a WHO introduction of antimicrobial resistance. So this is from the WHO website. If you search WHO and antimicrobial resistance, you should be able to come to this web page. And I highlighted here that why we are studying antimicrobial resistance is because it's one, or at least WHO declared it as one of the top 10 global public health threats that's facing humanity. And just to mention, others on the list are climate change, pollution, and vaccine hesitation, so stuff like that. For those of you who are not familiar with the name antimicrobial, probably you guys heard of antibiotic. So there's a little bit difference between those two. Generally, antibiotics are the substances that's naturally produced by microorganisms, and antimicrobials include both synthetic ones and the naturally produced one. But a lot of cases, people are just using those two interchangeably. And antimicrobial resistance is a problem because we, both the humans and the animals, and also in some crops, we are using, or we're overusing antimicrobials. So the antimicrobials are the pathogens, or are building resistance. So over time, the antimicrobials are less and less effective. There are some news. The left ones from FAO is kind of mentioning that antimicrobial resistance is likely going to be the next pandemic. So I think it's just trying to get some attention. And there are also others saying that antimicrobial resistance is a new climate change. So it do share some similarities with climate change, is that it needs global collaboration to tackle this challenge. And in some sense, yes, Sandeep?
Sorry, Xiaoli, are we supposed to see a different screen? I just see the title screen. Okay.
Somehow it's on my other screen. Sorry about you guys. Thank you, Sandeep. So here you are. I think I talked a little bit on that screen. And in the next one, this is what I'm mentioning, that it's kind of share some similarities with climate change, is because it needs global collaboration. And it's, in some sense, it's even more complicated than climate change, is because animals also plays a role here. That both humans and animals are using antimicrobials at the same time. So it's, as I mentioned, it's used in both humans and animals, and actually animals are using more in terms of the quantities more than humans. It's mainly because there are many more animals in the world than humans. However, overuse and those unnecessary use of antimicrobials in food animals is a key driver of antimicrobial resistance. And because of the global population increase, and also our demand for protein is likely also going to be increasing. So if nothing happens in the future, antimicrobial use in food animals is likely to increase as well. I have a figure from Shar, I'm not sure if I'm pronouncing name right, Shar et al. 2020, they had a rough estimate of the global antimicrobial consumptions. As you can tell from here, that's on the bottom, that's human consumption. And then above that, that's cattle, chickens, and pigs, fish consumption. And roughly humans are consuming 1/3 of the antimicrobials. In Canada, I think more than 80% of the medically important antimicrobials are consumed in animals. And I do have this figure from the Canadian Antimicrobial Resistance Surveillance System report. And unfortunately, I only have 2018 data. They haven't released 2019 and not even 2020 data. So this is kind of outdated. And you can tell here that especially tetracyclines are mostly used in animals. But there are also other antimicrobials, for example, the macrolides, and also there are others that's also used in animals. I have on the right corner here, have a comparison of the human and the animal population. So you can tell that animals are consuming a lot is because there's many more animals in the world or in Canada than humans. That's some basic data of antimicrobial use in animals in the last several years. Just a note here is that Canada had a regulation in 2017, which said, starting from December 2018, that all antimicrobials used in animals should be reported. So I'm kind of waiting for that data to come, but I think maybe that's also one of the reasons that we haven't have 2019 data. So this data here are reported by farmers. So it's only a rough representation of the actual antimicrobial use. And again, once the government released the 2019 and 2020 data, I think we will have much more information. And again, we care, or there's a lot of discussion about antimicrobial use in animals, or reduce antimicrobial use in animals so that we can save antimicrobials for human use. It's because the antimicrobial resistance, or the resistance genes can spread from food animals to humans through several routes here. That's indicated by the by FAO through farmers or the food, or even in the environment. And we can tell from here that the number of Salmonella isolate resistance to 6 or more antimicrobial classes is increasing. So I think in the human side, there's even report of people who are resistant to more than 20 antimicrobial classes. And there's, I think, more and more reports like those. So if the human is resistant to all the antimicrobial classes, then when there's infection, then the infection cannot be treated like it is very easily treated now. Let me talk a little bit more about the antimicrobial use in food animals. This is a table from Health Canada. I changed some terms a little bit. So basically, it classifies the different types, purposes, routes, or whether the antimicrobials are administered to individual animals or to group of animals, and then whether there's diseased animals already or not. So we can tell from here that the bottom two, the prophylactic and growth promotion use, are mostly or are all put in feed. So those were the feed routes, and metaphylactic here is a little bit tricky. So I think in Canada and US, we have a little bit different definition of metaphylaxis than the EU. So it's kind of having a not very vague definition here. So FDA said metaphylaxis is for disease control. So it could be either disease treatment or disease prevention. I think they're doing that in purpose here. So from here, we can tell that there's a lot, or not yet. I'm going to show you guys some data, but most of the antimicrobials are used in animals are through the feed route. There's a little bit from the injection and water route. And if you pay attention here, you can also tell that most of the antimicrobials are administered to a group of animals. And there's a problem with that is even the animals that's healthy is also going to be receiving antimicrobials. In humans and also in companion animals, only when we get sick, then we get antimicrobials. However, in food animals, if there's maybe like, for example, 10% of the animals in the pen that's sick, then all the animals in that pen will receive antimicrobials. Okay, so here are the quantity of antimicrobials by purpose. And again, here I don't have cattle. Somehow Canada only have data for the other several industries. Maybe one of the reasons is because the beef industry here is very powerful. But from here, we can tell that the growth promotion and disease prevention use of antimicrobial are still the major purposes of antimicrobial use. Technically, in 2018, there shouldn't be growth promotion use anymore because it's already prohibited. However, again, these data are farmer reported data. You can see that in 2018, there's still some growth promotion use of antimicrobials. And I had a summary of the group or individual treatment. So again, group treatment, all of the animals, regardless of their health status, will receive the antimicrobial. This is preferred by the producers is because it's economical. However, it leads to unnecessary antimicrobial overuse and it contributes to antimicrobial resistance. On the other hand, we would prefer those individual treatments, and we only treat those animals who are sick. However, that's not desirable for the producers because there's a lot of animals that's in subclinical status. It's kind of similar to COVID, where you might carry the passenger, but there hasn't been any symptoms. And if you're in a confined setting where many animals are together, and if you don't treat or if you don't administer antimicrobials to all the animals, then there may be, or there's a very high risk of disease outbreak. And this individual treatment is not favored by producers also because now there haven't been accurate, rapid and affordable diagnostic tools available to the producers. Okay, so a little bit summary of the antimicrobial administration route. For antimicrobials by injection, usually the dose is high and it's administered for a short period. However, there's a high cost, both labor and drug costs, but it's having high efficacy. If the producers mix the antimicrobials in feed, usually it's at therapeutic dose, and it's mixed in the feed for a long time. It's low cost. However, the efficacy of the drug is also low. Here is actually the data for the different routes of antimicrobials used in animals in Canada in 2018. And again, we can tell that 78 are in feed. And if we go back here, you can kind of read that it's the prophylactic and growth promotion use of antimicrobials. That's the feed route. Yes. Okay, so I will move on here. And injection is only 8%. There's 12% in water, and the other routes there's only 2%. So I know there's already a lot of research on the human side. However, on the animal side, there hasn't been many research on this. So in this research, our objective is trying to build a farm level model, and then we want to kind of simulate the impact of different antimicrobial use strategies on both the producer profitability and also the animal health. We also want to know the impact of different routes. For example, it's in feed versus in injection, to see if there's difference there. And lastly, we want to know if we take into account the externality cost of antimicrobial use in food animals to the human society, then will there be any difference of the antimicrobial use strategies? So we choose the beef feedlot sector as our focus of study, and we for the beef feedlot sector, bovine respiratory disease is the most economically important disease, and it's also the most common reason for AMU. So we actually modeled the BRD disease spread in feedlots. And for those of you who are not familiar with the beef industry, there are usually 2 or 3 stages of production. There's cow-calf and beef feedlot. Usually, sometimes producers also use antimicrobials in the cow-calf production. However, really beef feedlots where all the animals are confined in the pens, that's the stage where antimicrobials are used the most, and that's our focus for this research. I do have some data for the antimicrobials used in beef feedlots, and again, this is outdated. This is from a publication from 2019, but I'm really hoping that I can access to more recent data. So here on the right, those were the mass medication, and usually there are 2 antimicrobial classes that's used the most. One is macrolides, about 40%, and the other one is triglycerides, almost close to 60%. And an overview of our model, we have an agent-based and the SIR integrated model for disease transmission. And then we introduced antimicrobial management or antimicrobial strategies to manage the bovine respiratory disease. We basically have 2 types of decisions that the feedlot manager can adopt. One is the manager can decide which type of test to use. The other one is which type of antimicrobial strategies to adopt. I can talk about those 2 decisions in more detail in a little bit. And then in our simulation, we will keep track of the revenue, the costs, and the profit associated with different strategies. So for antimicrobial use strategy, there's 2 groups of strategy. The first group are the mass drug administration ones, or the group treatment. There were three sub strategies here. And for the strategies in this group, all the cattle in the pen will receive antimicrobials. However, these 3 sub-strategies differ by the route of antimicrobial administration. It could be only injection, or it could be only in feed, or it could be a combination of those 2. And then another group of strategies are the individual treatment strategies. And we assumed that for the individual treatment ones, there's only injectable antimicrobials. We exclude the water and the feed for individual treatments. Individual treatment means that the producer needs to pull out the diseased animals and then apply antimicrobials, which the diseased animals, in order to be isolated, need some support of diagnostic results. And there are 3 different diagnostic methods in our study. And the first one is what we call the conventional lab test, where samples will be collected from the cattle at arrival, and then they will be sent to a reference lab. We assume there's a 5-day delay for the result. And then once the results are available, then the feedlot manager can move the diagnosed cattle to the hospital pen for isolation and then inject antimicrobials. The second one is what we call the point of care rapid diagnostic test. There could be different technologies to achieve the test result. Usually for this test is on site and the results can be available very quick. Sometimes I think for some technologies, it can even be available within 2 hours. For this test, we assume there's a 1-day delay, and also for the rapid diagnostic test, the diagnostic cattle will also be moved to the hospital pen. And for the conventional lab and rapid diagnostic, the test can identify both the clinical and the subclinical animals. So it means that even if the animal doesn't have symptoms, it can be identified. The third one is where we assume only a pen checker was there to do the diagnostic. And the pen checker checks the cattle every day. And for the pen checker, only the clinical animals can be identified. The subclinical ones cannot be identified. That's the test and the antimicrobial management. I will spend a little bit time on the disease transmission model. It's a integrated model. We use the agent-based model integrated with the SIR framework. We choose the agent-based model is because it's a micro-level simulation model. It can represent those heterogeneous decision-making entities. So in our model, the agent is the cattle, and each cattle could have different weight, different disease status, and depending on whether there's antimicrobial use or the route of antimicrobial use, then the disease and the weight gain outcomes could be different. So there's a lot of heterogeneity there, and the disease transmission could be quite complex. And that's the major reason that we choose agent-based model. This is the outlook of our agent-based model on the left. You can see there's different types of cattle there with different colors, which represents their disease status. And if there's lines connecting to cattle, that means it is possible to transmit the disease. And one cattle could be connected with quite several other cattle. And on the right, those are the SIR model, and there were 4 different disease status, and the colors are linked with the agent-based model on the left. Let me show you. I hope this will work here. Let's see. So this is how our model runs. Let me go back here to the beginning. So from the beginning, you can see here, there's a lot of pink cattle, which are the subclinical ones. And usually once they arrive at feedlot, they will be treated with antimicrobials. And then you will be able to see instantly they will turn blue. That means they are treated. So here you can tell that they are all treated, and the red ones are the ones with symptoms. They will be moved to the hospital pen on the bottom. And then gradually there will be the pink ones again, the subclinical ones again. And then if antimicrobials are not used, then there will be more and more infected cattle again. And on the right, we can track different status of the cattle. We can track the number of them. We can also, it's not shown here, but we can also track, for example, weight or the cost and many different things here. So in our economic model, Sandy?
Xiaoli, those in the previous slide, if you go to the previous slide, so those black lines that connect the cattle, how do you get those parameters? Like there are so many different diseases and so many different infection rates. I'm not being critical. I'm saying it's very cool, but how do you get that?
Yes, so there was, it turns out there's a lot of studies about BRD. I guess it's because it's so so important, and they do have contact rate available in the literature, and we used that. So
so that one, so this is only for BRD?
Yes, this is only for BRD. And if you want to use this model for a different disease or different animal species, then you need to update the parameter, the contact rate, and also the length of connection.
Right. So when you look at this green, the picture on the left, so a line between two green cattle, is that just one parameter, the contact rate, or what is that?
No, so the contact rate is how many cattle is one cattle connected to.
Oh, sorry. So what is the length of the line then?
The length doesn't matter. So
okay.
It's only the number, how many cattle are connected to that cattle. The length doesn't matter, it's a distance. So you can imagine those lines should be invisible in reality, but the cattle, they move, right? If they move, then they might.
I get it. You're because the cattle are different by weight and other cattle attributes. That's why the connections are different. Is that right?
So it will refresh every day. So the number, the average contact rate is a parameter. However, every day there might be a new network there. I don't know, maybe some cattle have fixed relationship, I'm not sure, but in our model, we assume it's random. So every day there will be a new network there.
Oh, so this doesn't have any other parameter than just their movements? What is the parameter on that? That's what I'm having trouble with.
Let me see. I think I have that here. Let me see if I can find it. Is it here? Or contact rate here, the lambda is 2. It's calibrated from several sources, and then I think there's let me see. Yes, I think that's the parameter really deciding. I think we have another parameter, but probably not here.
This is just about their physical movements, and the infection rates and other things are introduced by the SIR component. Is that?
Sorry, what's the SIR component?
The infection rates and all that are introduced by the SIR component of your model?
Yes, so this is only the network, right, of the cattle.
I see, okay.
And they, depending on the weight and also when they arrive at feedlot, they might have different status. For example, some cattle after transportation, they might already sick, or that when the cattle arrive, they might have different weight. So those will all affect their disease status. And then it's kind of complicated depending on the antimicrobials they received. They might recover quicker or slower, or then that will also affect their weight gain. So it's kind of a interconnected.
Okay, thank you.
Yeah, here what we can really say from the video was just the connection, but there's a lot of things that's behind. For example, here, I think you can, here we have the different treatments, whether it's individual treatments or group treatments. There's other state charts that I didn't include here. Again, there's how does the animal gain weight? Henry?
Yeah, thanks. My question is kind of similar to Sandeep's. I guess I have very limited experience with agent-based models, and the one experience I have was with where the agents were farmers. So there it was pretty easy to look at heterogeneity. So, you know, they grew different crops, they have different farm sizes. So I guess I have two questions. One is, what are the different attributes that these different agents or animals have? And then my second question is, do you get anything from using an agent-based model versus just sort of random Brownian motion of the animals all just sort of bumping into one another? And would you generate a similar sort of network with just Brownian motion?
So the two most important attributes is weight gain, or weight of the animal. I think the producers care about that the most. And the other is a disease status. And then also, whenever a antimicrobial use, depending on different types of antimicrobial use were triggered, then that will also affect the weight gain and the disease status. So those were the two most important attributes in our model.
So weight gain is completely sort of like a fixed outside parameter, like this animal has this much weight gain and it's not related to the disease?
No, it's related to both the disease and the weight.
Okay.
So in earlier periods, when the cattle are younger, then maybe they're not as robust as when they're getting close to the end of the feeding period. I think we did model it quite several stages, depending on which weight interval they are in. Then they might be like there's some natural resistance to the disease. Some cattle, even they are contacted by diseased cattle, they might not have the they might not be sick. So yes, that's one. And really it's because of this complex disease model. There are a lot to be considered, and I don't think we can use the what you mentioned, a random Brownian, or so it's kind of really difficult to have what I call them equilibrium-based model, and you cannot solve the model analytically.
Okay, thanks, Xiaoli. That helps.
I have a little bit of a follow-up, and it's related to the Brownian motion. So if you go back to the previous slide,
this one?
It's a very naive question, actually. So are these cattle moving around and able to transmit the disease to other cattle?
Yes.
Yes, okay. So then this will give you an equilibrium, right? This will give you in equilibrium, how many are diseased, how many are not, and all of that, right?
Right. That also depends on whether you use antimicrobial or not, right?
Right. So my thing is that if you imagine there are only 3 cattle moving around, 2 of them diseased, all 3 of them are of different weights. Okay. So do you have information on how close, supposing one cattle goes to the other and shakes the other one's hand, for 3 seconds, it's going to transmit the disease. But if it just passes by, it's not going to. Do you have that information? How is the disease transmitted?
No, so because they're in a confined setting, right? The pen was not that large, and also there will be feeding time, right? So they all go through the same. How do you? What I'm not sure what that's called, but the same feeding space,
right?
And that's likely that they're going to be.
So the infection rates are not cattle specific, not based on their movements.
No.
I see. Okay.
No, no, we didn't take into account movement, like the inside the pen. It would be nice if there could be data supporting the different movement behavior, but we didn't incorporate that.
No, that's. I was just curious, James.
Yeah, could I stick my hand up for a moment? I just started at 3:30 and I don't know what's going on at all. The only movement is between the feeding pens they'd normally be in, and if they're ill, they're in an isolation pen, isn't it?
Yeah, yes. So between the home pen and the hospital pen is the one that's in clinical status that's going to be pulled up.
And the movements you're talking about is the 260 days or whatever it takes to get them from a 600-pound steer to a 1,200-pound steer. So essentially, my view of this, and I'm probably going to confuse things, is that if you take the SIR out, the agent-based model, each calf is an agent, and you have some sort of a differential equation that explains how they're gaining weight over time to get to the point that they can be slaughtered. And essentially, you then take the agent-based models and you put transition probabilities that determine whether they're susceptible, infected, or recovered, right?
Right. So the disease transmission probabilities are also depending on the weight and also several other things. And also for the movement, I think Sandeep is referring to the movement inside the pen every day, right, Sandeep?
I was referring to that.
Right. So our model is like every day it refresh, and then we might for 230 days. Then at the end of the period, we keep track of everything and then calculate the profits and all kind of characteristics of the cattle. And also because we have several quite different of testing methods. So depending on which type of testing methods we use, then different cattle can be pulled out to the hospital pen. So for example, the pink ones, if you use the point of care rapid diagnostic, they can also be pulled out. If that's the case, then I think really we probably don't need mass medication, and individual treatment probably is enough. If those kind of tests are cheap.
Okay, I think Xiaoli, you need to, if you have a lot of slides to show, you need to go on. I think. No?
I can. Anyway, in our economic model, it's really I didn't have a model that is solving the optimal decision every day. Instead, we have the feedlot manager choosing among strategies. So each strategy is a combination of antimicrobial use decision and also the test decision. We have 9 strategies in total. We have a no infection, where we assume there's no BRD, no disease. And then we have 3 individual AMU treatment strategies, depending on which of the 3 test method was used. And then we have 5 mass AMU strategies. So these are the 5 group treatments. We assume there could be just arrival injection. There could be arrival injection plus injection again at day 21, or the next two are there's no injection, just in feed. And then the last one is a combination of injection and feed. So different types. These are our mathematical model. There's a lot of variables here. I'm gonna skip. But basically here, the feedlot manager is maximizing profit, which are the revenue minus the feed cost, the test cost, the antimicrobial cost, and other fixed costs. Then there's two disease dynamics here. There are two state equations here. One is disease dynamics, the other is weight dynamics. And you can tell here, the disease is as it transit from one state to another. There is a P, which is the matrix there. It has many parameters there. I'm not gonna go to details there. But the next one is the weight gain. And again, the weight gain depends on the antimicrobial use. It also depends on the disease state. And we had a Monte Carlo experiment. We ran 10,000 simulations for each strategy. We have 9 strategies. And the length of the feeding period is 230 days. And then we collect data during the simulation runs. And this is my main result. So we, for the 9 strategies we study, I have here both the profit, the antimicrobial cost, the feed cost, and the test cost. And the first 3 that I highlighted here are the mass injection, or these are kind of the metaphylaxis ones. I call the arrival injection as the business as usual, BAU. So you can tell that these 3 strategies are having positive profits, and really the injection combined with feed is the most profitable one. It's probably because the antimicrobial injection at arrival controlled the disease, and then the feed in day 21 is likely gonna have growth promotion purpose there. So that's why that one is having the highest profit. And these 4 I highlighted here are all having negative profit. So the prophylactic ones are if you only administer antimicrobial by feed, then that's not enough for disease control. As I mentioned, it's probably because antimicrobial by feed has low efficacy. So think of if the cattle gets sick, then maybe the cattle will lose appetite, similar to humans, and maybe antimicrobial by feed in that case was not effective. And the next 2 are the individual ones. Really, if you only rely on pen checker, then the subclinical animals are going to be ignored. And conventional lab, there's a long lag, 5-day lag. By the time the results are available, it's probably already too late. You already have the disease outbreak there. And the point of care rapid diagnostic test here is having a positive profit. However, that's based on an assumption that the test price is $7.68. This is not the actual test price. So this is a price that I calculated based on a study where basically they, I think it's Bill and Melinda Gates Foundation. They have several biotech companies. They will try to develop those diagnostic test tools, and they set a goal of $5 per test. And then I converted that to the Canadian amount, and I also multiplied by the economic profit, which is likely, I think, 18% for those types of companies. I have the details, but I'm not gonna show them here. So again, though the previous results are based on the current antimicrobial efficacy. If we assume in the future that antimicrobial efficacy is going to be decreased, then you can tell even if the efficacy just be reduced by 25%, then all of those mass AMU strategies, those 3 injection strategies, they will have lower profits than the POC RD test. And if the antimicrobial efficacy is further reduced to, for example, it's 50% lower, then they will have negative profits. So if in the future the antimicrobial resistance issue continue to getting worse, then those strategies are will not be profitable anymore. And we also try to use information from literature from Ennis et al. 2020, who calculated the externality cost of antimicrobial use in poultry to the human society. So we did some conversion from antimicrobial use in poultry to beef feedlot, and then we also find another literature who, another paper, John et al. 2013, who finds that the antimicrobial administered by oral route is about 500 times more likely to incubate antimicrobial resistant genes. So we also take that into account. Then you can tell from here the externality cost through feed or water is much higher than through injection. Then here is the results with the externality costs. The last column, I call it net benefit. It's basically the profit minus externality cost. And we can tell from here that those antimicrobial strategies, those mass antimicrobial strategies, which have feed there, is having really like large externality costs. And the next one are the 2 strategies with positive net benefit. One is the arrival injection, and the other one is the rapid diagnostic test. So the BAU, the business as usual strategy, is having only slightly positive net benefit. And again, if antimicrobial resistance is gonna develop or getting worse in the future, then maybe that strategy will also have negative net benefits. And that leaves the POC rapid diagnostic test, the one with the highest net benefit in the several strategies that we studied. So I'm getting, I have several minutes. I guess I can conclude. Really, without externality consideration and with externality consideration, the results are different. And I guess I can show you guys here. These are the ranking of the strategies. This is the same results as I showed in my table. However, here you can tell that the one on the top, that's just by profit, and the one on the bottom is the net benefit. So injection plus feed is gonna lead to the highest profit. However, it is also having a really high externality cost. And the individual point of care rapid diagnostic test is gonna have the highest net benefit if we can achieve that USD $5 per test cost. If we can get to that, we can reach that target, then individual point of care rapid test will be the one that will lead to the largest net benefit. However, before we can reach that target, the business as usual, which is mass injection at arrival, that's the one, we can go back here, that's the one that weighs the highest both profit and net benefit. However, again, if antimicrobial resistance continues to get worse, then this strategy will no longer be profitable, not even mentioning the net benefit. And now there's more and more stringent regulations of antimicrobial use in food animals. And I mentioned that in Canada, starting from December 2018, that's all antimicrobial use need VAT prescription. And again, the companies need to report the antimicrobial sold, although we haven't seen that data. In EU, starting January next year, they are going to ban the prophylactic antimicrobial use. So those antimicrobial use in feed for disease prevention purposes is going to be banned from next year. And they also have more stringent regulation about antimicrobial injections. Anyway, so I think in the future, US and Canada might follow EU of implementing more and more stringent regulations. So from our results, there are some policy implications. First, the reason for antimicrobial use in feedlots is because of the cattle from the cow producers need to be transported to feedlots, and through that transportation, many animals, many cattle get stressed, and they also more likely to get the BRD. So that's the most important reason for BRD. And if there could be more vertically integrated beef industry, then maybe we will be able to eliminate that need for antimicrobial use in beef feedlot. However, that's another debate whether vertically integrated beef industry is better than the segmented beef industry. That's one implication. The other implication is that there could be policies to reduce unnecessary antimicrobials in food animals. Right now in Canada, we have already banned growth promotion use. And we have already required VAT oversight or prescription for medically important antimicrobials. Maybe Canada in the future will follow EU, also ban the preventative use of antimicrobials in feed. And eventually maybe Canada will also ban even the mass injection. However, I don't think the individual or the therapeutic purposes of antimicrobial use in food animals should be banned, is because there will be animal health and animal welfare concerns. In the US, they have a policy to incentivize those biotech companies, not the pharmaceutical companies. The pharmaceutical companies are not interested in AMU anymore because they have better ways of earning profit from other drugs. So there could be policies to incentivize the biotech companies to invest in the rapid diagnostic test technologies. And if the cost of those tests can be reduced, then maybe we don't need the mass drug administrations anymore. Then we switch to the individual antimicrobial strategies. And we have some future plan of maybe like moving from to incorporate more AMU strategies. Or in this study, we borrow the externality costs from another study. Maybe we can do a more comprehensive study on the externality cost. Or we can extend our model to a multiple year model, or maybe we can develop a optimization model. I think there are quite different ways of extending the model we're having now. So with that, I'd like to thank the Alberta Major Innovation Fund for funding our research, and I'm happy to answer your questions.
Thank you, Xiaoli. Any question? James?
Yes, James.
Unmute. You need to unmute.
Sorry, I came in about half. I came in at 3:30, so I've missed about half of this. But could you talk a little bit about the externality, and could you go back a couple of slides just before your conclusions? You know that table? That one, yeah. So the externality, I assume, is antibiotic resistance in people, is it?
Yes, so I actually have another slide. Let me see. I have it. Oh man, I have too much up here. Here, this one. So this is how they, Ennis et al., how they calculate the externality cost. Is basically the antimicrobial resistance in food animals that's imposed on the human society. It didn't take into account the externality cost of, for example, one feedlot manager used antimicrobial, then imposed on other feedlot managers. So it only take into account the externality to the human society.
And that somehow reduces overall income, and that's an externality.
Yeah. They're really, I think really we have pretty comprehensive study of the social cost of carbon, and I think maybe like a similar study can be done for antimicrobial use in food animals, but really this is the only one I find that I can kind of refer to.
So can you go back to the graph or to the table?
Mm-hmm.
And in the table, there's really only two things. There's, are we going to test for it after our injections? And the injections are, we inject each calf when it comes in with terramycin, or you do some combination of injecting them and putting it in the feed. So you're upping the amount of terramycin that goes in to their feed rations with each of those things. And that's where you get these huge externality costs, right?
Yeah, it's basically here I made a assumption, and again here, this is the study. There hasn't been too many studies here on how likely it is gonna be more likely to incubate antimicrobial resistance by feed versus by injection. And this one, they did a experiment in mouse, and they find it's 500 more likely. But again, I think if there could be another experiment on the beef cattle, and if they can provide the information on how likely it is going to be more likely to incubate antimicrobial resistance through feed, then we can use that information. So basically here, yeah, it's just a difference between feed and injection.
Yeah, and basically I guess it was the tetracycline. So you take all of the externalities out, and typically, really the only two things I think that you look at are the rapid diagnostic test profit versus just a single injection, right?
No, mass injection. The first row is mass injection.
Yeah, that everyone gets it. Every animal that gets into a pen gets it. Some of them just get a single one. Some of them get it twice. Some of them get an injection and they have it in their feed. Some of them only have it in their feed, right?
Right.
And I assume each of those are sort of upping the doses of the tetracycline.
So the dose are the same for each injection, and the same for each day in feed, but the feed and injection are different.
Okay, but why? What's the difference between injection twice and an injection? Is it just, are they getting one and then they're getting a booster shot?
Yeah, kind of like that. So the BAU, the business as usual, is just they get it at arrival, and then they injection twice. We're just curious if there's another injection at day 21, then maybe that will help or not. We did an experiment there.
Yeah.
Yeah.
But the injections seem to dominate the testing as long as you can do a rapid test. The rest kind of irrelevant. It's just too expensive or it doesn't work.
Right. Yeah. I mean, even now the rapid diagnostic test is expensive. This test price is what I use as the target price, that's the target cost that they mentioned.
And it's the externality cost that really just turns everything around.
Yes.
Okay. Sorry, that was just clarification. Thanks.
Thanks, James. Any other questions? I have a little questions.
Sure.
So you mentioned several strategies. I understand that you've taken into account the cost of several injection, the cost per injection, et cetera, et cetera. How did you account for the different labor cost? Because if you have to inject every animal versus another strategy where you don't, or it's a lot more expensive in terms of cost. Did you take into account that?
No, so we just use a single unit cost per injection. We assume it's going to be a large feedlot. So we didn't take into account, for example, if you have a larger feedlot and versus a small feedlot, then the labor cost might be different. We didn't take into account that.
Okay. Any questions? No? Xiaoli, thank you very much.
Thank you, everyone.
Thank you.